Hi again. In a previous video, I looked at the basic theory behind infrared spectroscopy, and in this video, I want to show you how I would start learning how to interpret IR spectra. Now the thing is, to be pretty good at interpreting IR spectra, what you really want to be able to do is be able to predict what a spectra would look like, or spectrum would look like. So maybe I might have mislabeled this. I should have called this spectra prediction. And if you get good at predicting how the spectrum will look like, then you'll be able to do some matching, just like we see in this problem here. Okay, it wants you to match the structure to the individual spectrum. Okay, but before I get to that, I do want to mention about the limitations of IR spectroscopy, which I didn't get to do in the last video. So for instance, if we have a molecule that we know has this molecular formula, we could probably get this from combustion analysis, but we don't know the structure. So let's draw two molecules that have this molecular formula. If through other chemical means we've narrowed it down to these two, then IR is great to differentiate these two. IR can easily distinguish. Because these two molecules have different functional groups. But let's say we understand that, we have an alcohol of this molecular formula, but we don't know if the alcohol has this structure or this structure. Now IR would not be very good to use here because it has the same functional groups. So IR, it's not impossible, but it's very difficult. So I would not use IR for this. In a different type of spectroscopy that you will learn later, you would use NMR, nuclear magnetic resonance, can tell the difference. The spectra would be very different. Very different, and actually, with a little bit of training, very interpretable. And all undergraduates who get through organic chemistry can predict and interpret the spectra of these two molecules. But that's in the future. Let me talk about IR. Now, again, an IR spectrum has several features. Wave number, or you could even think of this as a frequency, and you have peaks and signals that go downward. The bigger the peak, or the longer the peak, the stronger the absorption of that IR light at this, again, we'll call it wave number or frequency. But instead of having a bunch of spectra and trying to figure out what molecules these represent, a better way to go about studying is to be able to predict where certain functional groups will fall on the spectrum. So for instance, we're going to do a lot of these, and there are a lot of examples. And the first example I want to do is just a regular alkane. What would I expect if I have an alkane in the IR spectrometer? You have a baseline, and you have this very strong signal, strong and pretty sharp. Now don't focus too much on the number of peaks. That can vary because there's so many different vibrations in a molecule, so many different stretches and bends. We're not going to be able to account for every single signal. But a signal at this point here, and this will be around, well, let me tell you that this is a carbon that's sp3 hybridized H bond, and that occurs around 2900. inverse centimeter. Now don't get hung up on the exact number. It could be around 2900. It could be 2925. It could be 2875. Just this is just an approximation. And because it's fairly long, we're going to call this a strong signal. Okay. We're chugging down the spectrum, and at this point right here, kind of far down, this is at 1400, and this is the methyl group. I expect my students to know whether a molecule has a methyl group if they can hopefully spot a signal around 1400. Okay. And this would be considered either medium or weak. Again, it's going to vary depending on the conditions and the molecule, weak to medium. But strong, weak, and medium refers to the length. Okay. So I would predict it's a very plain molecule. It's a hydrocarbon. I would pick something like this. Now, most of your carbon-hydrogen bonds are going to be in this region. Okay, but that carbon could be sp hybridized, sp2 or sp3, or you can think of it as a carbon-carbon double bonds or triple bond. But the actual absorption here is due to the bond to the hydrogen. So these types of hydrocarbons, you'll see signals around 3100 to 2800. And the fact of the matter is, almost every organic compound you see is going to have a carbon-hydrogen bond. So you will see always a signal in this area. But there's going to be subtleties that we'll see a bit later. Now, if I extend the spectrum more to the right, we're going to cross over 1000 inverse centimeter. Anything to the right of it is going to be called a fingerprint region. And it's very unusual to look at signals in the fingerprint region and try to attribute that to structure because it's just a region of the spectrum that's very messy, and there are very few signals there that are interpretable. So, for instance, in this spectrum right here, below 1400 or below 1000, sorry, I really don't look very carefully in this region when I do an interpretation, when I try to figure out what compound I have. Look at this here, the non-fingerprint region. Okay. All right, so this is for an alkane, and this is our strategy for this video. We're going to pick out a couple of different molecules and try to predict the spectrum and pick up frequencies. Now, your textbook, most textbooks are very good at listing different frequencies, but the danger of that is if you're trying to memorize or even using the table to figure out whether you have a certain functional group or not, you're missing some of the subtleties, like the shape and the strength. Even though they're mentioned here, it's much better to be able to look at a real life example or be able to sketch it yourself. Okay, so that is our strategy to learn how to interpret an IR spectrum, is to be able to predict IR spectrum. Because, again, because of these subtle differences, just reading it off of a table may not be very helpful. For instance, an alkene. And the alkene I want to look at is this. Okay. Alkene, CC double bond. Yeah, we're going to have something in the CH bond region between 3100 and 2800, but this is fairly distinct that it's separated. That it's separated from this kind of jaggedy signal here. So what happened here? This is again the C sp3 hybridized H. It's a carbon that's tetrahedral, right, connected to a hydrogen. That bond is absorbing in this region. But this thing a little bit to the left, oh, by the way, we'll always list the frequencies so we keep track. The one a little bit to the left is actually the CH bond, but of a sp2 carbon. So maybe this hydrogen right there. Okay, that carbon-hydrogen bond is absorbing a little bit to the left of this junk here, and it's very close, but you should be able to distinguish it. It's at 2950, and it's pretty sharp. So not only do we have the length as strong, weak, or medium, we have sharp or narrow is another way that some textbooks describe it. Okay, and we'll see examples where it's not sharp. That's called broad. Now, if I ask my class to predict what the spectrum will look like or what you should be looking for when trying to find the spectrum for this molecule, we do have methyl groups, and again, I do expect students to know that a methyl has certain vibrations in this region, or that absorb in this region, 1400. Oh, you know what I forgot? Super important. The carbon-carbon vibration. Carbon-carbon, it's going to be a stretch uh, rather than a bend. And sorry about this. This is important because not much happens in this region except things that have molecules that have a double bond. So let me draw that here. We're going to call this a medium length or medium strength, medium signal. And this is the carbon-carbon double bond at 1650. So while carbon-hydrogen bonds are around 3100 to 2800, in this nothing, um, well, I shouldn't say nothing much, but things in this region, um, let's say around 1800 to 1550 or 1500, those are the double bonds. It could be a CC double bond, and later on we'll see that it could also be a C oxygen double bond. Okay, so look at our strategy again. You're picking up. You're picking up each of these numbers and correlating it to a bond, and then visualizing how it might look on a spectrum. Again, it's very similar to this, but now we're drawing the general shape. The general shape. Okay, let's keep on cruising. What I want to do next is, you know what? We went from a carbon-carbon single bond to a carbon-carbon double bond. Why don't we try an alkyne? That's a carbon-carbon triple bond. Yes, and eventually, you know, don't panic. Eventually, by doing all of this drawing, I know it's a lot of work, but all of this drawing will help us be able to interpret and match. This will be a lot easier. Okay, see, all of we all know that these signals here are the CH absorptions. Okay, all right, alkyne, an alkyne, an alkyne that has a terminal hydrogen. So we have that. Well, that carbon-hydrogen bond is going to be set off a little bit more, and it's going to be pretty sharp, and it's going to be pretty distinct. And here's the carbon-hydrogen bond for carbon sp3. Let's label those CsP3H. Okay. Eventually, I'm going to stop labeling the CsP3H, I think. But here we go. We had a carbon sp2 around 2950, but this is an sp hybridized carbon, sp. So this is, and particularly we're looking at this carbon with this hydrogen. Carbon sp, H, and that is around, whoa, 3300. So that's really set off. Now look where the carbon-carbon triple bond is going to occur. Not much happens in this region. This region, triple bond, this region around 2100. So around this region, you're going to find your triple bonds. And it should be pretty set off, right? 2100. See, nothing much happens in 2100, around that 2000 area. But if you do see something, then most likely it's going to be a triple bond, particularly a carbon-carbon triple bond. But another molecule that has a triple bond, and that is the nitrile, CN. That comes a little bit to the left, and I'm going to draw it right here. Okay. So this nitrile, that is 2250. But what does it look like? You know that it's this bond here, C triple bond N, and that is 2250. A little bit to the left. Yes, to the left. Again, this area around 2500 to 20 or 2000, think triple bonds. Okay, so far so good. Let us look at one other hydrocarbon that's super important. It's the benzene ring. You're going to have a chapter, if you haven't yet, that talks about benzene and all of its reactions and derivatives. It's a very popular molecule. DNA has a lot of benzene. There are a couple amino acids in your body that has a benzene ring. Many of the drugs, a lot of drugs have benzene in their structure. It's very simple because, we only have carbon and hydrogen and carbon-carbon bonds. And actually, we don't have any sp3 carbons in the plain benzene. So what is this signal right here? I think we know that signal already. That's the carbon-hydrogen bond when your carbon is sp2, 2950. There's something distinct about benzene itself. We have two pretty distinct peaks, and they occur at 1600 and 1500. So both of these are attributable to the CC bond, double bond, of a benzene. And this is 1600 and this is 1500. Now these subtleties, I know that we have something here that's 1650 of just a normal double bond that's not part of the benzene ring. All of these subtleties, it's very rare that a student would have to be able to predict or explain these subtleties for the carbon-carbon double bonds, depending whether it's a benzene or whether it's in just a regular alkene. All right, so don't worry about that. Just know it's in the general region over here. Okay, let us add a heteroatom, something other than carbon or hydrogen, and a lot of times we're going to have oxygen in your molecule. Oxygen is very interesting in an IR spectrum, or maybe not oxygen, but I should say the OH group, alcohol functional group, or you could even think of it as the hydroxyl group. Very close to the left, we're going to have a smooth, broad signal. That is the OH of an alcohol. And it is around 3300. Not much happens that far to the left, and it's typically a medium to strong peak. But this is our first peak or signal that is broad, not sharp or narrow. Very distinct. If you have an alcohol, a hydroxyl group, it should be pretty obvious. Now we have all of this carbon-hydrogen absorption. And I'm not going to write it down now. The absorbance, the frequency, sp3h. And what else? Oh, this is our first time we have a carbon-oxygen bond. So that carbon-oxygen bond is right here. CO single bond. And that is 1100. What is this? This is the methyl CH3 group. And I just like to put this because this represents the rest of the molecule on the left. So you have a methyl group, and we said 1400. All right, now here's a twist. I'm going to have a molecule that has an OH portion of it, but that OH portion is part of a carboxylic acid, not technically an alcohol. Why do they give them different names? Why can't they just say this is an alcohol with a carbonyl next to it? Because these have fundamentally different reactivities. You're going to learn different reactions for these two types of molecules. So even though both have an OH group, the reactions of alcohols are very different from the reactions of carboxylic acids. And the spectrum is going to be different as well. Because when you have an OH group next to a carbonyl and you have technically a carboxylic acid, that OH signal is actually going to shift. And it's going to shift to the right, and it's going to look very messy. Not smooth, definitely broad. What happened here? Well, due to the carbonyl group, the absorbance of the OH group gets shifted. It gets shifted to, do you remember from the last video? To lower energies. The lower the frequency, the lower energy light is being absorbed. But the fact of the matter is, for practical purposes, we got to know that all of that broadness is really an OH of a carboxylic acid. And it's very broad, so we really can't give it a defined number, but it's around 3000. Because we know that this little peekaboo, right, that is your CSP3H, and just as a reminder, that's 2900. So it's severe overlap between the OH of the carboxylic acid and the absorbance of the carbon-hydrogen bond. But there's one other thing that's very distinct about a carboxylic acid, and that's the carbon-oxygen double bond. Very sharp, very strong. I already mentioned something about double bonds. They occur in this region, just like a CC double bond. So where is the CO double bond? It's a little bit to the left, and we're going to say the CO is 1700, slightly higher than a CC double bond. Okay. All right, hang in there, guys. I have a couple more. Oh, before we move on from the oxygen-containing molecules, like the alcohol and carboxylic acid, let me show you. Oh, here it is. All right, let me show you how the OH shifts. Here we have cyclohexanol, and cyclohexanol looks like this. And here's your OH signal. What did we say? 3300? But when you have a carboxylic acid, like acetic acid, look how it's shifted, that broad signal. Now it's shifted here, and maybe you could, just in general, we could say that this area is the OH of the carboxyl group. And that is around 3000. And the OH here is around 3300. Okay, and see how it's that chunk is overlapping this, so you barely see it. Okay, it's underneath there. Okay, but also we have this one right here, the CO double bond, and we attributed that to 1700 inverse centimeter. All right, this will come very easily, I think, with some practice. There are two more spectra, and then I will let you guys go. The next one is a molecule with nitrogen. Very interesting spectrum for an amine. And technically, this is called a primary amine because it's connected to one carbon. It's interesting because you have an NH2, and the two bonds between nitrogen and hydrogen are actually visible as a double hump. And then we have, again, our junk, our carbon-hydrogen bond. CsP3H, but look at this. This is the NH2 group. And I like to think of it as a double hump, one for each hydrogen. That is around 3350. So it's like an hydroxyl group. It's like an alcohol, but again, alcohol absorption is pretty broad, whereas here we have a very distinct double hump, 3300 versus 3350. But we also know that amines and peptides, did I say amines? I mean amides and peptides have an NH bond. Okay, that's a peptide bond. You might have learned that in genetics or biochem, or even just plain biology. Well, how does the NH absorbance change when it's part of an amide? Well, it just becomes one hump. We have our signals for the carbon-hydrogen bonds. Okay, and again, we have a CO double bond. So that's going to occur around 1700. But, you know, there's a little bit of variation depending on what's next to the carbonyl group. In this case, this is again, the CO of an amide. And I'm going to go ahead and put a dotted circle around that. Does it change a lot? It gets pushed to the right a little bit, 1675. Okay, so it's kind of in between a CC double bond and the CO double bond of a carboxylic acid. I'm sorry, you don't see that. There. Let me get both on the screen. All right, and this, again, is just the NH bond of an amide right here. And we will call that 3400. Again, don't be married to these numbers. It could be 3450, it could be 3375. Okay. That's it. And I think I hit all of the main ones that will help you. We're not going to do this problem together, but your textbook, most textbooks are pretty good at explaining IR and giving you lots and lots of practice. So we have 6 molecules here. We have 6 spectra here. You should be able to match. Okay, and it's pretty simple. It's pretty quick sometimes. See, that's a hydroxyl group, OH. It's just dude right there. Done. Go on to the next one. Cool. Thanks for hanging out with me. It happens to be Valentine's Day today. So let me just leave you with this. Happy Valentine's Day. You know what you could do? You could look up these molecules and how would you draw or how would you predict the spectrum will look like for each of these molecules? Why don't you try that or just enjoy your Valentine's Day?